In the previous activities, you explored the basic vocabulary of networks, learned to identify IP addresses, observed packets with the ping command, and distinguished between switches and routers. You now have a solid mental picture of what a network looks like and how data travels from one machine to another. This course takes things a step further by introducing the Open Systems Interconnection Model, more commonly known as the OSI model, and the fundamental concept of encapsulation. These two notions are the backbone of all network communication and are essential knowledge for anyone working in cybersecurity or DevSecOps. Why a layered model? In the early days of computer networking, every manufacturer built its own proprietary systems. A machine from one brand could not communicate with a machine from another brand because they used completely different communication rules. This was a major problem as organizations needed their diverse equipment to work together. To solve this, the International Organization for Standardization published the OSI model in 1984. The idea was simple but powerful. Define a universal framework that breaks down network communication into distinct, independent layers. Each layer has a specific responsibility, and layers communicate with each other through well-defined interfaces. This allows engineers to design, troubleshoot, and secure networks in a structured and logical way. Think of it like a postal system. When you send a letter, you write the content, put it in an envelope, write the address, hand it to the post office, and the post office handles routing and delivery. Each step is handled by a different entity with a specific role. The OSI model applies the same principle to digital communication. The 7 layers of the OSI model. The OSI model defines exactly 7 layers, numbered from 1 to 7. Layer 1 is the lowest level, dealing with physical signals. Layer 7 is the highest level, closest to the end user and applications. Here is a detailed description of each layer. Layer 1. Physical layer. This layer deals with the actual physical transmission of raw binary data, ones and zeros, over a medium. The medium can be a copper cable, an optical fiber, or a radio wave in the case of wireless networks. The physical layer defines things like voltage levels, cable specifications, pin layouts, and signal timing. A network cable, such as an Ethernet cable, and a wireless antenna are examples of physical layer components. This layer has no understanding of the meaning of the data. It simply transmits bits. Layer 2, Data Link Layer. This layer is responsible for reliable node-to-node communication on the same local network segment. It organizes raw bits into structured units called frames. The data link layer uses physical hardware addresses, known as Media Access Control Addresses, MAC addresses, to identify devices on the same local network. A switch is a data link layer device. It reads MAC addresses to forward frames to the correct port within a local network. The data link layer also handles error detection to ensure frames are not corrupted during transmission. Layer 3, Network Layer. This is the layer you are already familiar with from previous activities. The network layer is responsible for logical addressing and routing, that is, finding the best path to send data across multiple networks. It uses Internet Protocol addresses, IP addresses, to identify source and destination machines globally. Data at this layer is organized into units called packets. A router is a network layer device. It reads IP addresses and decides where to forward each packet to get it closer to its destination. Layer 4, Transport Layer. This layer manages end-to-end communication between applications running on 2 different machines. It ensures that data is delivered reliably, in the correct order, and without duplication. The 2 main protocols at this layer are the Transmission Control Protocol, TCP, and the User Datagram Protocol, UDP. TCP provides a reliable, connection-oriented service. It checks that every piece of data has been received correctly, and retransmits anything that is lost. UDP is faster but offers no such guarantee. It simply sends data without checking. At the transport layer, data units are called segments, for TCP, or datagrams, for UDP. This layer also uses port numbers to distinguish between different applications on the same machine. For example, a web server typically listens on port 80 for unencrypted traffic and port 443 for encrypted traffic. Layer 5, Session Layer. This layer is responsible for establishing, maintaining, and terminating communication sessions between 2 applications. A session is a logical connection that persists over time, allowing a continuous dialogue between 2 machines. For example, when you log into a remote server, the session layer manages the lifecycle of that connection, opening it when you connect and closing it when you disconnect. Layer 6, Presentation Layer. This layer handles the translation, formatting, and encryption of data. It ensures that data sent by one application can be understood by another, even if they use different internal formats. The presentation layer is responsible for tasks such as character encoding, for example, converting text to UTF-8 format, data compression, and encryption and decryption. Transport Layer Security, TLS, which is used to secure HTTPS communications, operates at this layer. Layer 7, Application Layer. This is the layer closest to the end user. It provides network services directly to applications such as web browsers, email clients, and file transfer tools. Protocols at this layer include the Hypertext Transfer Protocol, HTTP, for web browsing, the Simple Mail Transfer Protocol, SMTP, for sending emails, the Domain Name System, DNS, for resolving human-readable domain names into IP addresses, and the File Transfer Protocol, FTP, for transferring files. The application layer is where the actual user data originates before being passed down to lower layers for transmission. A practical memory aid. To remember the 7 layers in order from Layer 1 to Layer 7, many networking professionals use the phrase, "Please do not throw sausage pizza away." Physical, data link, network, transport, session, presentation, application. What is encapsulation? Now that you understand the 7 layers, you need to understand how data actually travels through them. The process is called encapsulation. When an application sends data over a network, that data does not travel in its raw form from the very beginning. Instead, as the data passes down through each layer of the OSI model on the sending machine, each layer adds its own header, and sometimes a trailer, to the data. This wrapping process is called encapsulation. It is exactly like wrapping a gift. You put the item in a box, seal it, put a label on it, and put it in a larger shipping box with a shipping label. Each layer of packaging adds information needed for that step of the journey. Here is how encapsulation works step by step. At Layer 7, Application Layer, the user data is generated. For example, your web browser creates an HTTP request asking for a web page. At Layer 4, Transport Layer, a TCP or UDP header is added to the data. This header includes the source port and destination port numbers, as well as sequencing information for TCP. The resulting unit is called a segment. At Layer 3, Network Layer, an IP header is added to the segment. This header includes the source IP address and the destination IP address. The resulting unit is called a packet. At Layer 2, Data Link Layer, a frame header and a frame trailer are added to the packet. The header includes the source and destination MAC addresses. The resulting unit is called a frame. At Layer 1, Physical Layer, the frame is converted into a stream of bits, ones and zeros, and transmitted over the physical medium as electrical signals, light pulses, or radio waves. On the receiving machine, the process is reversed. This reverse process is called decapsulation. Each layer reads and removes its own header, passing the remaining data up to the next layer, until the original user data reaches the application at Layer 7. A concrete example of encapsulation. Imagine you are using a web browser on your laptop to visit a website. Here's what happens. Your browser, application layer, creates an HTTP GET request, get/index.html http/1.1. The transport layer wraps this request in a TCP segment, adding source port 52300, a randomly chosen port on your machine, and destination port 80, the standard port for HTTP on the web server. The network layer wraps the TCP segment in an IP packet, adding your laptop's IP address as the source, for example, 192.168.1.10, and the web server's IP address as the destination, for example, 93.184.216.34. The data link layer wraps the IP packet in an Ethernet frame, adding the MAC address of your laptop's network card and the MAC address of your home router, the next hop on the path. The physical layer converts the frame into electrical signals and sends them over the Ethernet cable or wireless radio waves. At every hop along the route, routers, switches, the appropriate layers examine and process the relevant headers. When the HTTP response from the web server arrives back at your laptop, the decapsulation process strips each header layer by layer until your browser receives the raw HTML content of the web page. Why does this matter for cybersecurity? Understanding the OSI model and encapsulation is not just theoretical knowledge, it has direct practical implications for cybersecurity work. First, most attacks and vulnerabilities can be mapped to specific OSI layers. For example, a denial-of-service attack that floods a network with traffic operates primarily at Layer 3 and Layer 4. SQL injection attacks happen at Layer 7. Man-in-the-middle attacks, where an attacker intercepts communications, exploit weaknesses at Layer 2, ARP spoofing, or Layer 3, routing manipulation. Knowing which layer is involved helps you identify the appropriate countermeasure. Second, tools like Wireshark, which you encountered in a previous activity, display captured traffic organized according to these layers. When you open a captured packet in Wireshark, you see the Ethernet frame, Layer 2, the IP packet, Layer 3, the TCP segment, Layer 4, and the application data, Layer 7, all stacked on top of each other. Reading this information correctly requires a solid understanding of encapsulation. Third, when conducting a penetration test or analyzing network traffic, you need to know what information is visible at each layer. IP addresses are readable at Layer 3, port numbers at Layer 4, and application content at Layer 7. Encryption at the presentation layer, for example, TLS, hides the content of Layer 7 data from an eavesdropper, but the IP addresses and port numbers at Layers 3 and 4 remain visible. Key terminology summary. Frame, the data unit at Layer 2, containing MAC addresses. Packet, the data unit at Layer 3, containing IP addresses. Segment, the data unit at Layer 4, TCP, containing port numbers. Datagram, the data unit at Layer 4, UDP encapsulation, the process of adding headers as data passes down the OSI layers on the sending side. Decapsulation, the process of removing headers as data passes up the OSI layers on the receiving side. Protocol data unit, the generic term for the data unit at any given OSI layer. Conclusion. The OSI model provides a universal language for describing how networks function. Its 7 layers, physical, data link, network, transport, session, presentation, and application, each handle a specific aspect of communication. Encapsulation is the mechanism by which each layer adds its own information to the data as it travels from an application down to the physical medium, and decapsulation is the reverse process at the destination. These concepts underpin every protocol, every tool, and every attack you will encounter throughout your cybersecurity and DevSecOps training. Mastering them now will make everything that follows significantly easier to understand and apply.